Let me start with this slide, okay? Give you a quick introduction of Binghamton. So, more than 100 years ago, that's the birthplace of IBM. And of course, today we know it's globalization is the word to describe IBM. Now, that's more than 100 years ago. So a little less than a year ago, Professor Stan Whittingham received the Nobel Prize in chemistry. That's we, as a colleague of him, we're all very proud of him. Okay. So the middle is the picture of the campus, the main campus. Okay. All right, so today I'm going to talk about nanoscale chemistry and catalysis and sensing. This sounds like two topics, catalysis and sensing. What I like to do is reunify the theme is with the nanoscale chemistry. So I'm going to talk about separate about catalysis and sensing, but one of the central focus is nanoscale chemistry. So I like to use this graphic outline to talk about what is the important thing that motivated us to in the field of catalysis and electrocatalysis. So that's on top panel is the energy, particularly emphasize clean and sustainable energy. One of the ways to do that is convert solar energy to electricity. You can store the electricity in a battery, or you can convert them to hydrogen fuel, and from hydrogen fuel, you can utilize a fuel cell. And the key here is this pathway really allow us to increase the hydrogen to carbon ratio in this sustainable transition to zero carbon emission, right? That's the future, okay? That's the way we're going from, as illustrated, top right corner, we increase the hydrogen to carbon ratio. Now you can see the future will be the pure hydrogen. That's really our goal, right? Our goal. Now, what is the reality? The reality is fossil fuels, right? We're currently using fossil fuel cell. We're going to use this for a certain period of time until one of the days, it's going to be no more fossil fuels. But that's reality. So we have to deal with the fact we have to clean the pollution. So we have to develop emission control systems. The catalytic converter in the cars is one of the ways to eliminate the emissions, right? So there's an increasing challenge also in that particular area. So what is the chemistry? The chemistry here is the dynamic nature of the catalyst. Catalyst is really our focus. We focus on non-noble metals and the noble metals. So basically the goal is we want to reduce the noble metals, right? And I want to re-emphasize, I'm going to give you a few examples today, is with the nanoscale chemistry involving dynamic evolution, causal structure, and those types of things as illustrated in this graphic illustration here. Secondly, we're interested in sensing, right? Chemical sensing, biosensing. So we're also using nanostructure interfaces. And in this particular, we want to develop portable, wearable, wireless sensors for healthcare, for environmental monitoring of pollutions, right? All these kinds of applications. So one of the ways to do it here is using biological systems such as antibody antigens to capture the target, such as biomarkers in cancer and other diseases, right? So here we illustrated here is a microfluidic detection scheme for cancer biomarker detection using nanoparticles. So we also use by manipulating the particle size, composition, surface properties, particularly as illustrated in the bottom left, right bottom, lower panel, is the manipulation of the interparticle properties for detection of molecules, biomolecules. So that's with the kind of chemistry we to emphasize. So this, so I'm going to give a few examples in the next few slides. So the first four is the scale chemistry in catalysis. So we have many chemical reactions, and here illustrated two class of examples. You know, the first class of example is oxygen reduction reaction in fuel cell, right? As illustrated here, one of the things is reduce oxygen to water. And this is one of the important reactions in fuel cell cathode. And then I'm going to illustrate some examples later on to talk about the chemistry we're interested in. Second part is the catalytic oxidation in gas phase, such as CO oxidation, but also hydrocarbons such as propane, toluene oxidation, and etc. So those kind of reactions involve gas phase reaction, particularly involve oxygen. Okay, this is something I'm going to highlight in the next few couple slides. You know, the oxygen plays a major role in terms of activation of this catalytic oxidation reaction. So here's one of the first examples. In this particular example, I want to talk about the catalytic oxidation reaction in gas phase, and in particular reaction illustrated here is the propane oxidation. The propane oxidation, one of the things we know is involve oxygen, right? So under oxidation conditions, the surface of nanoparticles, a catalyst, particularly illustrated here is a platinum alloy with non-noble metals such as nickel, cobalt, etc. So those kind of metal has a propensity of oxidation to form a surface oxygenate layer. So I'm going to talk about what is the role of this particular oxygen surface oxygenate layer. So in this particular slide, on the top panel illustrates a platinum nickel cobalt ternary nanoalloy particle. This particle is oxygenate. The surface layer of 5 layers or so are oxygenated. So as illustrated here, you can see the sharp contrast between the core and the shell. It's totally different, right? The lattice is also different. Then you look at the middle, illustrated by the yellow highlighted region. So we can really manipulate the degree of oxygenation. So one of the ways to do that is to introduce, you know, temperature control and concentration of different concentration for oxygen. So we can call it shallow oxygenation, as illustrated in the left-hand side, or deep oxygenation, as illustrated in the right-hand side. So, but this particular illustration, really, we can actually confirm that using X-ray diffraction study, as illustrated very far right panel, is when we reduce them using hydrogen, we have lattice shrinking. When we oxygenate, we can see the lattice expansion. So we can basically do those kind of lattice shrinking, lattice expansion reversible. Okay, this process is reversible. We can do this all the time. Now, the bottom panel illustrates the metal oxygen coordination. One of the things I want to highlight is this, you know, the oxyphilic metals such as nickel and cobalt. That basically takes the responsibility of oxygenation, minimize the oxygenation of platinum. So that's really one of the important things for this particular nanoalloy structure. You know, the oxyphilic metals take the responsibility of oxygenation rather than oxidize the noble metal. That's very important in many catalytic reactions because we rely on the reduced state of noble metals. Here's in the top panel is a typical catalytic activity illustration. It illustrates the propane conversion as function of temperature. You can see the nanoalloy with much less, 70% less of platinum, and it shows catalytic activity is higher than pure platinum. In the insert, you can also see if you raise the loading, you can actually see even higher than the pure platinum. So one of the things is about oxygen, right? So what is the role of oxygen? And we, in this particular, in the lower panel of this slide illustrate, we try to illustrate is this: if we first oxygenate the nanoparticles, then we introduce the propane without introducing oxygen. Then we see is the oxidation of propane. So the only source of oxygen is coming from the lattice oxygen, the surface or lattice oxygen, as illustrated on the right-hand side. So the red color atoms are the oxygen species, oxygenated, oxygen species in the surface of the lattice. So demonstrating the surface of the oxygenated nanoparticles play a major role in the catalytic oxidation reaction. That's unique. That's unique for the ternary nanoparticles. So now we want to do is we want to understand the detailed mechanism, the detailed nanoscale chemistry. So we use in situ operando techniques in this case. As illustrated in the top corner, you can see this is a in situ operando measurement setting here. In this particular setting, you can see we can have several techniques. We can have synchrotron X-ray, and so we can do diffraction. We can also have infrared light. We can do diffraction, diffuse refraction spectroscopy, infrared spectroscopy called drifts. We can also do mass spectrometry. We can detect the product and the reactants change. So this propane oxidation thing I want to illustrate here, we can collect accessible data. So we can collect drifts data. That's the spectroscopy, infrared spectroscopy. We look at the reaction surface species. In the middle is the high energy XRD. We can do pair distribution function analysis, the PDF. We can analyze the metal bond distance and ordering, disordering, and phase structure. The lower part is the mass spectrometry. We can detect the reactant and the product change. So I really want to focus, narrow the focus to the middle panel. It's really the major result, showing the top is the detect surface species actually increase as function of time during the reaction. And more importantly, those species demonstrate a type of regular or irregular, a mixed oscillation, okay? And then if you look at the crystal structure in the middle, in the D, you can see they also display a certain degree of oscillation. The red color is strongest intensity, the yellow weak, the blue is the weakest one. You can see it also oscillates, the metal bond distance. In the lower panel, you can detect the product. If you really zoom, to look at the product, you can also see the oscillatory behavior. So really this set of results really illustrates the surface size is highly dynamic, and particularly the oscillatory behavior really illustrates not only the surface size is highly dynamic, but it's also crystal structure is also highly dynamic. Okay, that's really the key point I want to emphasize from this in situ operando study. Now, the next part is we want to illustrate in a fuel cell reaction. So in the fuel cell reaction, we want to illustrate it is also highly dynamic, the surface size. As illustrated in this particular slide, you can see if we prepare a nanoparticle, nanoalloy structure in the middle, then during the reaction, we can have a different kind of phase segregated core shell structure, dynamic evolved core shell structure, or structurally different core shell structure, etc. So those kind of things, in order to understand this thing, we load the catalyst in a fuel cell. Then we examine the catalyst change as a function of time during the operation of the fuel cell reaction. Okay, particularly emphasis is placed on the oxygen reduction reaction as illustrated here. Now, before I show you in situ operando data. I want to show you a set of data using thermochemical treatment of nanoparticle. Starting point is a bimetallic noble metal nanoparticle, gold platinum. This particular nanoparticle, the two metals are not subject to de-alloying, so they're very stable. The stability allows us to restudy the activity, the structural change. And the one thing illustrated in the middle is you can see that when you raise the temperature to 800 degrees, the gold enriched on the surface form a core shell structure, the catalytic activity drops. So you can use a thermal chemical treatment. In the bottom, using a plating copper nanoparticles. In this case, although we don't have much surface enrichment here, but we'll see a phase structure change. The surface is enriched with the FCC structure in comparison at a higher temperature treatment, in comparison with the core structure, BCC structure. And if you do computation, DFT modeling, you can show actually the activity for the FCC structure is higher because it has lower kinetic barrier. Now let's show the in situ operando data. Okay, operando data. This is a set of data. We put the catalyst in the fuel cell as illustrated in the bottom. Then we measure the diffraction as a function of time. Then we process data, look at the intensity change. I want to really draw your attention in the circular area is the intensity oscillates. Okay, the PDF peak oscillates, indicating the metal-metal bond distance. The metal-metal bond distance, actually during this catalytic reaction, electrocatalytic reaction, the oscillates. This oscillation actually provides us information to understand what is going on. So what is going on? As illustrated in the right-hand side, we can see there's basically de-alloying and re-alloying. So if there's no re-alloying, they're going to form this kind of phase segregated structure, like the platinum skin, platinum shell, and a platinum shell or platinum nickel core. And then what we discovered is all this, because of the oscillation, because of de-alloying and re-alloying, allows nanoparticle to restructure. That's really the key point here. And this key point is confirmed by synchrotron X-ray diffraction data because we didn't see any phase segregation. Okay, we only see alloy structure. So this oscillation really is indicative of the de-alloying and re-alloying process in the dynamic process. All right, so this is a final set of data for this first part is the nanowire. We're using a platinum ion nanowire catalyst. Putting the load in the fuel cell. This particular catalyst is very high activity as illustrated here, and also very stable for up to 120K cycles. The activity only drops about 30%. That's truly remarkable for this type of catalyst. Then we loaded the catalyst in the fuel cell, the nanowire in the fuel cell. We look at the catalyst, look at the lattice parameter change. One thing we noticed here is this: they never go to phase segregation. They also occur, as I illustrated the previous slide, undergo the de-alloying and re-alloying process. Okay, this process allows you to achieve, allows the nanoparticle to achieve restructuring, and de-alloying and re-alloying, as illustrated in the far right panel. Okay, so process you subject de-alloying, leaching of the base metal ion, then you're re-alloying for the remaining metals inside nanowire, and ultimately to the very, very stable state. All right, let me switch gear a little bit, okay, towards the nanoscale chemistry and sensing, right? That's I know my time I still another 10 minutes or so. That's more than enough time for me, okay? So so in this case, I like to illustrate very recent work. This is a work just recently published. Basically, we use nanoparticles to construct fibrous sensors. So we load the nanoparticle as illustrated in the in this left-hand side, you can make an electrodes in the sintering. You sinter the metal nanoparticle, then you form electrodes inside the fibrous structure. Then subsequently, you can load chemically sensitive nanoparticle on top, surrounding all the fibers, okay? Then you can develop a sensor. So this process you can do, you can sinter the metals on the surface of the fibrous materials, or you can penetrate, across the fibrous materials, because the fibrous materials are highly porous materials, allows you to do that. So here's one in situ capture of this surface morphology. From left to right, you can see as you drop the nanoparticle on the surface is black. As time goes, after about 30 seconds, it's almost golden color. And then if you go to prolonged time, it's a golden color, it's much shiny. So this process is a sintering process, demonstrating this is at room temperature, okay? Room temperature allows sintering occur in a very effective way. Actually, we did, in this particular paper, we did Gibbs-Thompson simulation to look at how the temperature approaching room temperature using all the nanoscale parameters, and theoretical data and experiment data actually showed quite a good agreement. Okay, that's where we're pleased with that. Okay, now to make a fibrous sensor, so you basically, as illustrated in this slide, you can in the bottom you can make the electrodes. You can print the electrodes, in the fibrous materials. Then subsequently you can print the sensing film on the electro printed fibrous materials. Then you can actually, as illustrated in the right panel, you can actually develop a sensor, chemical resistor sensor. This chemical resist sensor illustrates, here's two examples. This is where we explore the interparticle properties. When the molecules, such as alcohol molecules, as illustrated here, different channels of alcohol, CO, CO2, to enter the interparticle spatial confinement. They're going to introduce intermolecular interactions. Those interactions change the electronic properties. Then we can detect the response in terms of the resistance change. So that's really one nice illustration demonstrating the nanoscale chemistry works very well for a sensor, fiber sensor. And one of the particular things I want to emphasize, the fiber sensor is very, very sensitive. You can also do things like this, okay? You can, as illustrated there, you can, the nice thing about room temperature sintering is you can use a paper, okay? Paper substrate, because, conventional sintering is all at a high temperature, more than 100 degrees, and now the paper can survive those kind of temperature. And then now another technique is using laser. Laser, you can introduce high temperature, but it's highly confined, okay, localized temperature, as illustrated in the middle here. This profiles is simulation to really look at the temperature profile region. This red zone, as illustrated here, is really only in the thin film nanoparticle area. There's no penetration to the substrate, so you can nicely control that. So we made some devices on plastic substrates, like a PET. We can also make this thing on paper substrate. And if you load it with sensing film, you can see the response. Because the fiber structure, the sensitivity is so much higher than a PET substrate, the fiber structure. Okay? That's very important discovery. Then I also want to illustrate this to you is we can use nanoparticle on this kind of fibrous or flexible sensors to make a strain gauge sensor. Okay, the strain gauge sensor, you can bend the sensor in different direction as illustrated at the top. There you can have a response with this is all nanoparticle structure. You can, depending on the bending direction, if it's parallel to the electrodes, you can see the response is smaller. If you have perpendicular to the electrodes, you have a response is much greater. And that's very intriguing. We call it anisotropic gauge sensor, okay? So that's very important nanoscale chemistry. Also, from the interparticles spatial properties change, you can actually, we did quite some simulation demonstrates this chemistry works extremely well. Okay. So in this particular slide, I'd like to show you is we can use this kind of chemistry, nanoparticle structure, fibrous sensor, make it wearable, put on the devices, on your skin as a patch, or use it as a breast sensor. So breast sensor, sweat sensor. So that's really low cost because you can use the fibrous, cellulose fibrous structure, right? You can do this. And then one particular example I want to illustrate here is using dendronized nanoparticle. So because one thing about dendromone is that have multiple structure, okay, on the surface. You have hydrophilic, hydrophobic, this kind of structure. If you use this kind of structure as in the particle spacing, okay, spatial structure, you can actually introduce all kinds of tunability of the particle molecular interactions as illustrated in the very low part of this diagram, this slide. So we actually demonstrate that, okay? So at the very top, we can use this sweat sensor. We basically make this, the fiber sensor, put in a patch, then we apply to the skin on the human body. We can actually detect, the sweating, in terms of exercising, not exercising. We can, in the middle, we can also see, we can use it as a breast sensor. We can actually, this particular example actually demonstrate is the black was green. Is actually is two types of cancer. Lung cancer people, the gray color one is the patients with the breast sample from patients with lung cancer. The green color is actually samples from healthy people, the breast, and they can very nicely separate. Yeah. We can also use it as a simple, just detect the bruising, right? The bruising pattern. You can see illustrated in the bottom. We can put in the mask, and we can bruise it. We can very sensitive, the sensor, and also depending on is normal bruising or deep bruising, and the response magnitude is very different. Okay, very different. All right. So final example is we use this nanoparticle as a platform to detect cancer biomarkers. So basically, we bioconjugate nanoparticle with magnetic particle, gold nanoparticles to form those kind of so-called hotspot. The hotspot allow you to detect Raman spectroscopy in terms of enhancement. Okay, there's all those magnitude enhancement. So that's, and you can also use the magnet to concentrate the nanoparticles, because the magnetic particles, the super paramagnetic particles, allows to reversibly being attracted to the magnet, so you can achieve concentration. And the hotspot, as illustrated by the theoretical simulation, is in between the particle. It has a strong enhancement of electromagnetic field, allows the detection limit, lowering down the detection limit. Here's one example. So you basically want to detect CEA. CEA is a cancer biomarker. You increase the concentration, you see the signal increase, and you plot the data, and then you can actually identify, in this particular example, the detection limit is about 0.1 picomole. That's really the lowest, not the lowest one. The lowest can go to femtomole. We recently have data. Because we have not published that yet. So that's really the direction we're heading to. All right. So summary. Instead of using a text to provide a summary, I want to use a graphic summary here. So I started by illustrating the two pictures here, right? And the left hand side is the catalysis. So what is nanoscale chemistry? Nanoscale chemistry is a nanoparticle, the alloy structure, the atoms inside the nanoparticle is highly dynamic. In catalytic process or electrocatalytic process, they undergo evolution, alloying, realloying, dealloying, and surface size change. Those are the things are very interesting. Now that's the kind of things happening on and in the nanoparticle. On the right-hand side is really the interparticle spatial property. You can introduce different molecules as illustrated in the far right, from inorganic to organic to biological, all this kind of molecules allows you to actually manipulate the inner particle spatial property. Any perturbation of this chemistry, inner particle spatial chemistry, give us sensing signal. And this sensing signal is greatly amplified because of the nanostructure. So that's really provide us a platform for develop highly sensitive, highly selective, low detection limit sensors. With that, of course, I'd like to thank all the students, all the postdocs, all the collaborators, and including the funding agency. Okay, I want to thank you for your attention.